Hi everyone. At the end of this video, you should be able to calculate the sum of both infinite and finite geometric series. So we're going to start with a quick warm up. I know we couldn't calculate the sum of an infinite arithmetic series, but I want to talk about why you can for geometric. So let's say you have this series 1/2 plus 1/4 plus 1/8 plus 1/16, and you're summing that to infinity. Typically, people think if you sum an infinite amount of things, it's going to go to infinity. But that's not the case here. So I like to think about this like you're thinking about pizza. You have half a pizza, then a fourth pizza, then an eighth of pizza, then a 16th of a pizza. If you continue to sum that forever, what do you think is going to happen? Okay, I'm going to draw a little visual to go along with this. Maybe a square pizza here. So we start with a half a pizza. Here's half. Then we add a fourth pizza. Then we add an eighth of a pizza. Then a 16th of a pizza, so on and so forth, and we keep repeating this pattern. What's going to happen? So what is the sum of this infinite geometric series? Well, I'm just going to leave you to ponder that, but it is possible. So what we're going to do is figure out the formula to sum these, because obviously nobody wants to sum all the numbers from 1 to infinity by hand. So I'm going to give you the formulas in this video, although we will be able to derive them at another time. So the sum for a finite geometric series is as follows, and the sum formula for an infinite geometric series is as follows. So I'm just going to show you how to apply them in this video. And we're going to start with finite. So for a finite geometric series, you're going to take the first term times 1 minus the common ratio to the nth power, which is, how many terms there are, and then 1 minus the common ratio. Let's try one of these problems together. We're going to try this second one over here. So to find the sum of this finite geometric series, we need to know the following things. We need to know our ratio, we need to know what n is, and we also would want to know what a1 is. Okay, so remembering the explicit formula for a geometric sequence, this is our r. It's our common ratio. Okay, n is how many terms are in our series. So our n is 100, and a1 is the first term. So we can just plug in 1 to figure out what that is. So it'll be 1 minus 1, which is 1/2 to the 0, which is 1. So our first term is 500. Okay, now to find the actual sum, we can plug into our finite formula. So it's a1 times 1 minus 1/2 to the n, which is 100, over 1 minus 1/2. Last thing we need to do is just calculate this. Remember your order of operations, PEMDAS, and I'm going to pause to do the calculations. Do them on your own. I'll come back with the answer. Okay, I plugged this into my own calculator, which I actually will display for you here, kind of. And if you do it correctly, you should get 1,000 as your answer. So if you sum all of the terms in this series from 1 to 100, the sum will be 1,000. Cool. So that's all you need to know for how to use the formula. Again, we can go back and derive where it comes from later. Okay, I'm leaving the other one for you to do on your own, and I want to move on to an infinite geometric series problem. Okay, so a lot of people are like, why can't I just use the finite formula? So I'm going to kind of show you something here before we get started. We'll do this first one together. So let's say I wanted to use the finite formula on this. It would be a1 is 1 times 1 minus the common ratio to the their infinite amount of terms, so that's my n, over 1 minus 1/2. Again, to get the first term, I just plugged in 1 here. So 1 minus 1 is 0. Anything to the 0 power is 1. Cool. So let's see what's actually happening with this. Let's take care of the exponent right here. So what's 1/2 to the infinite power? Which is saying 1/2 times 1/2 times 1/2 times 1/2 an infinite amount of times. Well, if you multiply 1/2 by 1/2, it's a fourth, times a half, it's an eighth, then a 16th, then it'd be a 32nd, then a 64th. Notice as you multiply more and more 1/2s, this is getting infinitely small. So if I actually do 1/2 to the infinity and multiply 1/2 an infinite amount of times, it's going to be so small that it's insignificant. So if this is so small it's insignificant, this is my formula. Okay, it's just the first term times 1 minus nothing, okay, over 1 minus the common ratio. Okay, so that's actually where you get this formula. Notice it's just like the finite formula, except you don't have this. And that's because this term becomes so insignificant as you multiply an infinite amount of the common ratio. So if you want to see the connection between those, it's really an easy way to derive it. Now I hope I slightly raised a red flag. Let me say for a second that this common ratio was like 2. Because if you raise 2 to an infinite power, it does not become insignificantly small. 2 to the infinite power is actually a really, really, really big number. So let's think about this for a second. If my common ratio is like a number that's not between 0 and 1, and it's a number that when you raise it to an exponent, it gets larger, like 2 would get larger, 4/3 as you multiply that an infinite amount of times would get larger. So not just a fraction versus a whole number, but like a number that's between 0 and 1 versus larger than that. Okay, let's say that this happened. Would you be able to sum the infinite geometric series? So if my series was 2 to the n, okay, your first one would be 2 to the first, plus 2 to the second, plus 2 to the third, plus 2 to the fourth, so on and so forth. Would that have a sum? Okay, it would, but the sum would just be infinity. Or even if it was 4/3 plus 4/3 squared plus 4/3 to the third, again, that sum would be infinity. So the only time you would have an infinite geometric series is when the common ratio is a number between 0 and 1. Okay, like this problem I gave you from the start. Okay, the common ratio is each time you're multiplying by 1/2. That's what I was kind of just talking about. So this will have a sum because you're adding things that are getting smaller and smaller and smaller. So if you're adding things that are smaller each time, your sum will not be infinity. But if you're adding up large numbers, your sum will be infinity. Okay, so let me summarize what I'm saying here by saying you can only find an infinite geometric series, or the sum of one, if r is between 0 and 1. Actually, so maybe I can even write that like this. 0 is less than r is less than 1. Okay, or it could also be between -1 and 0. So -1 is less than r is less than 0. Right, because if you had -1/2, -1/4, -1/8, it'll be the same sum as the positive version except negative. And we can write this more concretely as the absolute value of r has to be less than 1. These mean the same thing. You guys should be able to use your knowledge of absolute value to figure out how those mean the same thing if for some reason you're not sure right now. Okay, anyways, I said all that just to show you that we can find the infinite sum for this, and the formula is derived from this formula. So let's actually go ahead and solve for it now. So we need to find our first term. Okay, so I do that by plugging in 1, and we already did this before, so you should know that's 1. And then we need to know our common ratio, which again is 1/2. And then we just have to plug into this formula. So it's 1 over 1 minus 1/2. Okay, which is really just 1 over 1 minus 1/2. So it's a whole minus 1/2 is just 1/2. And when we divide fractions, we should know by now that that's multiplying by the reciprocal to cancel that out. Whatever you do the numerator, you have to do the denominator. So the sum of this infinite geometric series would be 2. Okay, so what I did all of right here was actually the calculations for finding the sum. Everything I was doing before was just to kind of prove where this formula here comes from. It comes from the finite formula, but kind of simplified because this would become insignificant. So that is how you find the sum of geometric series, infinite and finite. And there are 2 problems for you to try on your own, and then a couple word problems for you to try in the back. So I want you to try those on your own, and I will show the answer in just a bit. Okay, I just wanted to give you the answers to the on your own problems from the front. So there are your answers. Hopefully you can take a look at your work and figure out either if you got them or what you need to do to fix them. And here are the